Hello, and welcome to our next session in today's virtual event. Just a quick reminder that you can ask questions by typing them into the questions tab. We'll take questions at the end of the session, and if your question is not answered, someone from the Neo4j team will reach out to you directly. With that, I'll hand the floor over to Lance Walter, CMO at Neo4j, who will introduce our next presentation.
Our next speaker is Dr. Jesús Barrasa, and he's been with Neo4j for a little more than 5 years in consulting and industry solutions role. Jesús has a very deep background in ontologies. He spent more than 6 years at Ontology Systems as a semantic data systems lead. Dr. Barrasa also has a master's degree in software engineering from ENST Paris and a PhD in AI and knowledge representation from Universidad Politécnica de Madrid. He is really maybe one of the most qualified people in the world to talk to us about ontologies. So to now get into the financial industry, business ontology, and the role that graphs can play, welcome Dr. Jesús Barrasa.
Thank you, Lance, for this introduction. Yes, I am Jesús Barrasa. I'm been quite a while with Neo4j, and I'm joining you from London. Yes, today I'll be talking about knowledge graphs, and being more specific, I'll be talking about a particular artifact that can be part of your knowledge graph, which is an ontology, ontologies. And even being more specific, I'll be talking about the FIBO ontology and how you can get value out of it with Neo4j. I suspect that it's a familiar topic for many of you, but in case you haven't heard about it before, the FIBO ontology represents a consensus of the common concepts as they're understood in the industry and as they're reflected typically in data models and message standards. So it stands for Financial Industry Business Ontology, and it's maintained by the EDM Council, which is formed with a number of large financial institutions. So it's a public, I would call it standard, and that's what I put the focus today. I'm hoping that, I'm probably going to move to my first slide. So I said that I'm hoping that if you're in that stage where you're exploring what graphs can do for you, or if you become aware of these open standards or probably ontologies like FIBO, and you think they're important, they're valuable, and you want to understand how you can leverage them in your data architecture, or even if you've already decided that building a knowledge graph is something you in your strategic goals, but then maybe hopefully some of what I will be saying today will help you spark a conversation with your colleagues or the people in your organization. But please, and that's important, feel free to reach out. We love graphs, we're huge graph advocates, and we love talking about this stuff. So I'm sure there's a member of the Neo4j team that I'm part of that will be willing to help you in this super exciting journey. So just a bit of background on my experience in these areas. So there's kind of a mixed feeling when we talk to organizations, and I've been doing that for a few years, as I was saying with Neo4j, that have started or initiated some kind of initiative in the semantic technologies, ontologies space, and it's this feeling that it always feels like that there's little tangible out of it. So it's always like a vision, it's always like a strategy, it's always in the future. What I want, and hopefully we'll be able to do today, is explain how, while there is always a component of strategy and vision in ontologies and this approach to data, there is immediate value that you can get from them, and Neo4j can help definitely accelerate you getting this value and adopting them in your data architecture. So that's my plan for today, and if the demo gods are with me, I hopefully should be able to even show you some of that in action. So just a little bit of context, because I'm sure you've heard about all these projects before and all these fantastic knowledge graphs. There's a bunch of industrial knowledge graphs out there that are powered by Neo4j, and I've just brought these three kind of star projects, like the NASA one, where they built a lessons learned knowledge base out of documents coming from multiple different sources, and they brought them all together and linked them together. Not only the documents themselves, but the content, the entities the things that were mentioned in these documents in a way that they could be queried in a complex way to answer sophisticated questions regarding lessons learned from previous missions, all sorts of projects that otherwise would be scattered across multiple sources, multiple silos of information. So it's a great story that they've been very open and talked about it in some of our events. So I invite you to go and watch the presentations in our YouTube channel. At the other end of the spectrum, we have projects like the one with eBay that are using, that have built a knowledge graph to back their conversational e-commerce platform. And probably the most popular of them all is the Panama Papers. I'm sure you've heard the story a couple of years, 3 years ago, this team of journalists that got data leaked from a law firm in Panama. And they had the fantastic idea of analyzing that data using graphs. So they brought all that data in Neo4j, and they managed to uncover all sorts of cases of corruption, wrongdoing involving politicians all over the world. So the impact was massive, and it was in headlines for months and months. Actually, it's the only knowledge graph, as far as I know, that got a Pulitzer Prize, which the team of journalists at the ICIJ got in 2017. But enough of that. What's behind knowledge graphs? So what's the concept behind it? So if you look at the way we've been building applications and storing data for the last N years, we've been putting data in relatively unsophisticated, factual data stores, right? And normally most of the knowledge, most of the logic, most of the intelligence was in the application. So what we propose with knowledge graph, the way I see it, is that let's push some of that knowledge into the data, closer to the data. Let's make it data. Let's make it explicit, rather than being hidden, implicit in the application logic. And if you're lucky and it's documented, then you might be able to use, to understand, to make evolve. Let's move from there to getting it closer to the data and make it explicit, because by doing that, we're going to get a number of benefits. But before that, let me elaborate a bit on this idea. So think of a data source. You have a number of tables that can be, I say in tables, but think of any type of data storage. And we have customer information, we have product information, you have your product portfolio, you have all sorts of information organized in tables. And you have application one that, for example, produces a report for your management or for regulatory purposes. And in the logic of that application, we find that if you combine the customer table with the product table, with the product catalog table, well, you can produce a report. But where's that logic? Where's that knowledge? Well, it's hidden in the application logic, right? And probably it looks like a 10-page horrible SQL query. Then there's application 2. And application 2 probably does some kind of customer segmentation. And similarly, they look at customers, the products, the type of products, and they look at similar customers and they produce some sort of segmentation. But again, where's that logic? Where's that knowledge? Well, again, it's implicit in the application. And we can go on like that forever. I mean, there will be application 3 that might be even using exactly the same logic as application 1. And it's combining data to produce, let's say, customer product recommendations, anything. Again, the same problem. The knowledge is hidden in the application. It's implicit. What we want to do is, and let me continue with the animation here, is elevate your data. Let's make that context explicit. Let's make that knowledge explicit. Let's bring these connections into close to your data. Let's make them part of your data. Let's make your data a graph. And let's enrich it also with explicit descriptions of your domain, ontologies. And here's where I'm going to link with the FIBO ontology. And ontologies that we're going to see happen to be a graph as well. Let's enrich it also with algorithms that leverage the structural nature of your data, because now data is a number of connected data points. It forms a network. And this structure can be leveraged by algorithms that focus on graph data. Well, there you go. You have a knowledge graph. You kind of built a knowledge graph out of your data. And as a consequence of that, you're going to be able to have much more lightweight applications, because now the knowledge, now the intelligence is in your data. you have a knowledge graph. So what are some consequences of that? Well, the obvious one, we've already seen that there's a reduction in the duplication of application logic, right? So instead of having every application replicating the same logic, now we have it in the graph, right? And there's advantages to that, because you can repurpose that data. Now it's much richer data. And keep in mind that you're investing in probably one of the most important assets, your data. I mean, I think these days, in the 21st century, we all agree that data is one of the most valuable assets that organizations have. So you're building knowledge, you're building value into this asset. And one kind of side effect is that by making all your understanding, all your domain knowledge explicit, you're going to get extra insights about it. You're going to get a great understanding of it. Right. So we've talked a little bit about ontologies. Let me spend a couple of slides explaining what they are and why are they relevant. So I don't want to be academic on this, so I'm going to give you the most basic and simple description of what an ontology is. An ontology is a domain model. So it's a representation of the entities in your domain. Right? If you're in finance, you will be describing financial products. You will be describing how they relate to each other. You will describe what are their characteristics. So all this description is precisely an ontology, but it needs two additional properties, as you can see on the screen. So it has to be a formal description. So what I was describing before could be just a piece of documentation. But one thing that makes ontologies different is that they are formal, and they're formal because we want to be able to use them in an automated way, to be able to programmatically leverage them, to get value out of them in that sense. So formal, that's important. And typically, they are shared. I mean, we're going to be talking today about the FIBO ontology, which is practically a standard, a common vocabulary, but you can have your own enterprise ontology that basically encapsulates the knowledge or the canonical representation in your organization of certain entities. And the reason for that is because one of the main purposes of ontologies is to enable interoperability, be able to exchange, to have applications communicate with each other by speaking the same language, right? So these three elements describe an ontology. So there are domain model, has to be formal, so that we can then programmatically use it, automate tasks using it. It has to be explicit, so it has to be an enumeration of the entities and the relationships between them, which is a graph, and it has to be shared, typically shared, right? So that's an ontology, simple as that. So, and there's a few very popular out there. Today, it's all about FIBO, but you probably have heard about schema.org, which is the one that Google Knowledge Graph uses. There's a standard from the Dublin Core Metadata Initiative that have general vocabularies for metadata management, but they also have some for education and bibliography. There's a huge corpus of ontologies in the life sciences, biomedical, biological. But what does an ontology look like? So here's what it looks like. So this is an ontology will be expressed typically in the RDF standard. That's a W3C standard for data exchange, right? And RDF can be expressed in a number of ways. There is an RDF version, which is the one that we have in front of us here, but there's JSON-based ones and several different others. So all this to say that here we have the formal element of the ontology. So we can parse it. We can have our code. We can have our applications using that. But let's look at the content. So there at the top, we see that there's a description of something called a privately held company. Well, that's an entity, that's a category, right? It's described as a class, as you can see, right? And it contains some human readable description of it as well. And below we have another block that describes a stock corporation, right? And stock corporation is another category of entities, and it has some characteristics. And if you go back to the first, to the description of the privately held company, we see that there's a line where we're specifying that a privately held company is a subclass of a stock corporation. So there's, as you can see, I'm drawing the graph to the right. So an ontology describes entities that are nodes in a graph and relationships between them. If we keep going, we're saying that a stock corporation is connected to another type of entity, which is a board agreement, through a relationship that's called is governed by. So that's what an ontology looks like. Well, this is just a fragment of it. What it really looks like, it's probably more something like this, and this is the view in Bloom. So FIBO in particular contains a few thousand definitions of entities, classes, relationships, properties, etc. And again, if we zoom in, we will see something like what we were just saying before. So you see there a fragment of a definition of what a corporation is, what a jurisdiction is. And what's great about an ontology, one of the reasons for it to exist, is the fact that we can now have the best of both worlds. We can have this visual exploration component, which we hopefully are going to be able to try hands-on in a minute, that will give you additional insights in your domain and give you an understanding of how these entities relate to each other. But at the same time, you can programmatically express queries like the one you have there. Let's say, for example, I'm trying to model and I want to follow FIBO standards, FIBO terminology, how to represent the jurisdiction of a non-profit corporation, right? So I could explore that visually, as you can see in the graph to the left. But I can also write a formal query in Cypher that would return exactly what's the connection between these two entities. We'll come back to that. So how are they used? I mentioned before this idea of interoperability. So we're making explicit this knowledge so that we can share it between applications and we can have them speak the same language, so that we can have consumers and producers speaking the same language and simplifying interoperability. That's point 2 there. But there's also what I was saying before. I mean, an explicit description of your domain will help you getting insights out of it, getting a good understanding of it. So that's more for human consumption in a way. And that third one, and probably the more interesting one, is the more advanced, is where you want to take ontologies as they are, which is actionable knowledge fragments that we can use to carry out programmatically tasks on our data. And I'm going to be looking at 2 of the most common ones, which is, for example, checking the integrity of your data. Let's say an ontology in a way, since it defines how things, which entities are in a domain and how they relate to each other, we can see that from the point of view of a set of constraints. So if your data does not align to this description, then we can highlight that as a violation of the domain of the ontology that we have described. So that's one way in which they can be used. And they can also be used for inferencing purposes, which is essentially to be able to derive new knowledge and new facts from the ones that we have. Right. So first one, insight, and that's going to give me a segue to get into showing you a little bit of Neo4j in action. So when we have a domain model that we can explore and that we can visualize, that will give us extra insights into it and will give us a good understanding of it. And we will be able to combine the visual element with the kind of structural querying element. Let me show you what I mean by that, and I'm going to jump into Bloom for that. So maybe in some of the previous presentations or in other events with Neo4j, you've seen Bloom before. So Bloom is our data exploration, visual exploration tool. And it offers an interface that's pretty simple. I mean, I'm not going to do very advanced things. There's plenty of cool stuff that you can do. But all I want to show is some of the elements that we've been looking at in the deck. So I've already loaded the FIBO ontology into Neo4j, and it's worth mentioning that we have a connector that makes it a one-click operation. So you literally have to point at the repository and just get all the data into Neo4j. The input is straightforward in the sense that we've seen that FIBO is a graph, Neo is a graph database. So the kind of translation is direct. But let's look at we're looking at stock corporation. Type it properly. So as I type, Bloom is detecting that there is a class called stock corporation, which I'm going to select. And I'm going to expand it to see what other entities does it relate to. So I see that it's connected to other entities through different types of relationships. And we have this SEO, subclass of relationship. So we have a number of nodes that are a subclass of stock corporation, right? So we see that stock corporation have 3 different subtypes. One of them is exactly the one we were looking at before, the privately held company, right? Remember that on the slide? So if I double click on it, we can see a human readable definition of it. We have also how they connect to other elements. So I can keep expanding here and see that the stock corporation is itself a subclass of a corporation, and a corporation relates to other entities through, let me see that, maybe domain and range. Domain and range is how relationships connect to entities. For example, we can see that a corporation can be constituted by, and we can see what's at the other end, a constitution. Well, surprisingly, there you go. Anyway, so all these, I wanted to show that we can use the visual exploration tools, and Bloom in particular, to understand your domain and see how the entities relate to each other. And at any point in time, we can click on the unique identifiers of the entities to jump to the EDM Council page. Oops, I wasn't expecting that to come like that, but not a problem. So well, anyway, you see that there's a human readable page generated that they maintain, and that contains all the information about these privately held companies, right? Perfect. Okay, so I think we're good with that. Let me actually go on full screen again. This click has broken a little bit there. There we go. No problem. And back here, so we were saying that the other example that we were looking at, just for completeness, let's clear the scene. And we were looking at how, I believe it was not for profit organizations, so something like similar like that, not for profit corporations. And again, there's an entity that describes that. We wanted to see how they relate to, I believe it was their jurisdiction, right? So we can search for the jurisdiction, and we immediately find the entity describing the jurisdiction. And one of the things that we can do is find a path that connects them. These will find the shortest one. That's not necessarily need to be the shortest one, but we find that they relate to each other in this particular way. So a not-for-profit corporation is actually a type of corporation, is a subcategory of corporation that happens to be connected with the jurisdiction through the incorporated in relationship, right? There you go. So well, that's how you can visually explore your domain, the entities in your domain, using Bloom. We could even extend the ontology from Bloom. I wouldn't say that Bloom is an ontology editing platform at all, but why not? I mean, you could, for example, look for a, let's say, loan or credit account, and you can say, well, it is the type of account. That's a subcategory of a financial service account, and we might be able to say, well, okay, I want to create a node that represents a new class. So what I'm doing here effectively is, okay, that's the FIBO ontology, but maybe I want to link my enterprise ontology to the FIBO one. So what I'm going to do here is, okay, let me edit my node, and I'm going to say, well, this is a loan account. And I'm going to set this value in the name property. Then I'm also going to give it a unique identifier, which is the URI, and I can probably use my own namespace. So I can say that's my organization.com, and that's my financial vocabulary, and I define the term loan account. And we can also give it maybe a definition. We can describe a loan account is blah blah blah, and so on and so forth, right? And when we're good, right, we can say that that's we've finished editing, and we have a node here that we can now link to the one defined in FIBO, and we can say, okay, let's create a relationship of type subclass of, right? Oops. Wrong way. Anyway, get the idea, right? So we can visually extend it and link our own enterprise ontology with the terms in FIBO. Good. So I think that's enough from the point of view of insight. So we see how we can get a good understanding of the domain by exploring it visually exploring it in Bloom. Now, the second one I was mentioning was interoperability, right? So we want to be able to use the FIBO model or our enterprise ontology model as the language to communicate between applications. That can be through APIs, that can be using specific data models. So one thing that we can do is align my data model, the model in Neo4j, with public ontology, let's say, for example, FIBO, right? So I'm going to define mappings between the elements in my graph, and my graph does not need to be defined based on FIBO initially. Maybe it's on legacy data store that we have, on legacy data set that we have in our organization, but I want to be able to expose it and present it in a way that FIBO RDF consuming applications can get value out of it immediately, so we can have instant interoperability with these type of applications. Let me show you quickly how we would do that. So let's get to that in a minute. So I won't go into it, but we have a little application that will help you define this mapping and say, for example, when you find an element in my model, I want to map it to the FIBO ontology. I want to map it to my enterprise ontology. So there's that. So what we are going to see here, and I'm going to do that from the browser, is first spend 2 minutes looking at our model. So this model is a simple data set with loan data. It's one of the public data set available from the Kaggle platform. And I think it's data from the Lending Club. It's a pretty simple model. Let me show you what it looks like. So it has loan accounts. So if I click on a right. So if I click on loan accounts, I get a bunch of them. For each one of them, we have a bunch of properties describing the loan, like the interest rate, the revolving balance, the loan amount, and so on and so forth. And each loan account will be, sorry, I come from Bloom and I'm clicking in the Bloom style. So there you go. So an account will be connected to the borrower, which is, in this case, we just have a borrower ID. It's anonymized data, obviously. The borrower is connected to the account through the borrower's relationship, and the account is associated to a zip code, and the zip code will have other accounts in the same area, and that's going to explode because I've probably picked a very populated area, but this is a zip code in the US that happens to be in California, right? So there you go. So just a quick view of the model. So this is a standard database in Neo4j with loan data. But as I was saying before, I want to be able to expose it, to present it to RDF FIBO consuming applications according to that particular standard. I've defined these mappings, which I'm not showing a second time today. But here's just a test, a browser extension that can generate HTTP requests to my browser, to my Neo4j instance. So what I'm doing is I'm calling my local Neo4j, and I'm saying, find me that particular loan account, which I'm searching by ID, right? So if I send this request, you see that if everything goes fine, and so far so good, we've been lucky with the demo, we see that it's presented as RDF, and it's described according to the FIBO ontology part of it, and that's interesting because maybe you want your model to align partially with FIBO, but use some enterprise ontology specific elements, and that's what we're doing here. So some of the elements in my model are mapped to my enterprise ontology, I call it EO, and some of them map to FIBO, right? There we go. So this is, again, an out-of-the-box element that you can get just by having your data stored in Neo4j as a graph. Good. Back to the slides. So we've looked at insights for human consumption, understanding of your domain by visually exploring the domain model, the ontology. We've looked at interoperability very briefly. Now let's look at the third and probably more sophisticated use of ontologies, which is trying to automate tasks based on them. So trying to use them as actionable pieces of knowledge. And the first way that I was mentioning before is use them as a tool to validate a data set, a data model. So the FIBO ontology is published in a number of formats. So at the moment, it's not published as a set of constraints, but there are tools out there that will help you translating it into Shackle. Shackle is another standard of the W3C for defining shapes, in a way, in your graph. So to define what your data is supposed to look like and what a violation of that structure should look like. So let me show you a little bit of that. So again, let's go back to the browser. Hope there's not too much jumping between screens. So right. The first thing we'll do is, well, load these constraints, right? So we have loaded the FIBO ontology, but I was saying that we can translate the FIBO ontology into a set of formal constraints. Let me show you what that looks like. And actually, I'm going to run it live to give you a real feel of what it's like and the time it takes. So the FIBO ontology defines a few thousand entities I mentioned before. So once it's translated into constraints, into graph shapes in the shackle format, and that's exactly what I've done. So I'm loading it, as you can see, from my hard drive. It's saved in my FIBO directory under shapes.ttl. So if I load this set of constraints, it's going to take a couple of seconds. So what I'm doing is I'm loading into Neo4j an actionable version of this ontology, right? So I'm going to be able to run these constraints as rules on my data, and that's what constraints look like. So we have plenty of entities. So we have, for example, a definition of exchange rate. So exchange rate is a category that has a property that's called hash-based currency, and that has a minimum cardinality of 1. And it has also a maximum cardinality of 1. So if you take these two in combination, basically what we're saying is when you have an exchange rate in your data, it has to have a base currency and only 1. And if you have more than 1, then that is a violation of the shapes, of the constraints that we're applying according to FIBO on our data. Good. Well, you've seen that the FIBO constraints are approximately 2,000 rules like this one. You can see down here. And it's taking just a few seconds to load them in Neo4j. Now they're loaded in an actionable form, so we can run them on a model. And we're going to run them on our model, the loan data model. So how do we run it? And let me again do a copy paste from my sheet here, so that I don't make any silly mistakes in the demo. So what I'm going to do now is I'm going to run a validation. So I'm just calling the method validate and producing the output. I'm limiting it to 100, and let me show you why. So if I run the validation, what Neo4j is doing is checking all these constraints, the 2,000 that we've loaded, against my data, and it's going to raise any violation of them. And we see some of them. For example, here we see that a borrower, I mean, basically all the borrowers, and that's why I stopped it, every borrower is expected to have an is played by relationship, right? That's because the FIBO ontology implements, this role modeling pattern where you have two different entities representing the customer and the customer as a borrower, or maybe the customer also as a lender is in another role. So because of that, when you model a borrower, you expect to have this other entity. This is informative, and that's what the severity indicates, which means that it's something that I may or may not want to comply with. So I can decide to filter and just keep the ones that are actual violations, right? And that's what I'm doing with this additional constraint. So if I run it and I focus only on violations, hopefully we should see that there's no violation of the FIBO constraints in my data set, right? Perfect. So no results, no violations. But now I'm going to force some of them. And what I'm going to do is one of the things that are defined in the FIBO ontology is that there's some disjoint categories, which essentially means that if you're in one side, in one category, you cannot be a member of the other category. And that applies, for example, to loan and credit accounts. So if an account is a loan account, then it cannot be a credit account because these are two disjoint entities, right? So what I'm going to do is intentionally introduce a mistake in my data, an error in my data, right? Let's say, for example, that in this particular zip code, and I'm going to pick one randomly, this 917, whatever, I'm going to take all the loan accounts and I'm going to tag them all as credit accounts. So I'm going to say introducing this violation. So I've just, now we should have a bunch of credit accounts as well. which are also loan accounts, right? So they have this dual labeling, loan account and credit account. So this, of course, goes against the rules. So if I rerun my validation, this should be picked up, and hopefully, if I've not made any mistake. Now, there you go. So we see that all these loan accounts are being picked up as a violation of this particular rule, which is a constraint that basically imposes that if you have a loan account type, then you cannot have this type as credit account. So here's a great example, and of course, you see that this is I've run them right live on a 1 million node data set. It's a few thousand constraints. So it's I'd say it's pretty performant. Of course, the engine is clever enough not to run them all, but just the ones that are relevant to the data set that we have, of course. But these are the internals of how it works. But what I'm focusing on today here is on the fact that we're using the knowledge in the FIBO ontology to carry out automated tasks like this validation, and this can be done as a batch process, like I've done. So I run it on this data set and highlight and report on the validations. Or I can run it transactionally as well to keep my data consistent over time. So every time someone writes, every time any process writes to my graph, to my Neo4j graph, I'm going to check that what I'm writing to the graph does not contradict any of the constraints. And if it does, I will roll back the transaction and prevent you from writing it. So it can be used in that way as well to prevent you from introducing inconsistencies. Good. So let me conclude, where was I? Good. So with just mentioning, I'm not going to show it in demo, the last way in which we could also leverage ontologies from an automated use point of view, and that's by using inferencing. So again, if you remember this idea of pushing some of the knowledge to the graph instead of having it in the application logic, essentially what I mean by this inferencing is that you can have a query, for example, like this one, that returns all your accounts for clients in the state of New York, right? And because there's a number of different types of accounts, and I'm taking FIBO terminology, you can have a loan or credit account, you can have an investment account, transaction, deposit, and so on and so forth. You might need to enumerate them all because I want a report that contains all my accounts. Or you can say, hang on, I think I have a description of that in FIBO, and I have it already in my graph. So I've made that knowledge explicit, right? And it looks something like that. So you have an account, and you know that account can be broken down in ledger account, bank account, etc., etc. So this is already knowledge that I have. So why don't I, instead of enumerating it myself, I call a general purpose method that will look at the ontology and say, well, you want accounts. I can understand what account means, and I can break it down in all the possible variants of accounts and give you the results. So the difference is that now the knowledge is not in your query. The knowledge is now in your graph, and it's being leveraged by this general purpose procedure that we're invoking. I think I'm going to make a stop here because I'm probably running out of time, and I would like to take some questions, but just a couple of takeaways. So there's always this, as I was mentioning before, these mixed feelings of we're embarked in a semantics project, but the value is going to be months, years away. So I hope I've shown you, given you some ideas of how you can leverage these knowledge artifacts right here, right now. So you can get Neo4j and you can use them in the way that I've shown today. I would recommend, be agile. So start small. You can get value from these ontologies that you have, public ones, the ones that you have in your organization. And as I started at the beginning, reach out to us. We'd love to help. And that's it for me. Any questions?
Awesome. Hi, Jesus. This is Greta.
Hi, Greta.
I have a couple questions from the audience. So,
excellent.
How are customers using FIBO or other ontologies?
Right. Well, we have a bunch of customers using ontologies. Actually, I've been personally involved now in one or two projects, but I would like to probably mention there's the Financial Times in the UK. So they're using ontologies to annotate their content, right, the articles, and use that for classification, for recommendation. And actually, they've been pretty open, and they've talked at some of our events, and they talked a couple of years ago in Graph Connect, and I think there's presentations from them in our YouTube channel, in particular from Dan Murphy. There also in the finance space, there's a great presentation and a great project by Nathan Maines, right, from Thomson Reuters, who are also using graphs in a number of ways, and ontologies in particular for managing reference data. There's many more probably in other industries, especially in the life sciences. There's the European EBI, European Bioinformatics Institute, that use Neo4j, have used Neo4j and are using Neo4j to create this lookup OLS, ontology lookup service, which is an index with a huge corpus of ontologies. So we have a bunch of projects. So I think it's a pretty interesting area.
Very cool. Can ontologies like FIBO be used in combination with Neo4j graph algorithms?
Absolutely, yeah. I only touched briefly on the graph algorithms on our graph data science library, but the beauty of ontologies is that they are. I mean, we've seen that they're part of your graph, so it's knowledge that's been made explicit in your graph. So it's actually, it will provide you, let's say like that, additional dimensions to understand and query your data. And what you will be doing with algorithms, with the graph data science library, is, for example, create different types of projections based on the ontologies and how you can classify your data according to them. So yeah, I think there's plenty of opportunities for these to collaborate together.
Oh, very cool. Can Neo4j be used as an ontology editor?
Oh, well, that's probably because I show how you could create a. I mean, I wouldn't call it well, no. Let's be clear. It's not an ontology editor. I mean, Neo4j is probably more the backend. I mean, you can store ontologies. You can. We're more on the operationalizing of ontologies, on the making them actionable, using them in automated ways, in programmatic ways. You can also use Neo4j to explore them visually. I mean, you can annotate an ontology. You can modify your graph from Bloom, but I wouldn't call it an ontology editor. There's some others out there, but it's an interesting question, and it's something that people will be hearing about soon, because we've been involved in a project with a big German company that we'll be talking about soon. That has been collaborating with Web Prodigy to create a Neo4j-based backend for their ontology editor. So that's, so Neo4j as such, no, but it can be the backend, it can be the platform on which an ontology editor could be built.
Very cool. And let's take one more. Does Neo4j offer a complete implementation of the shackle constraint language?
It's not complete. So it's not complete. First of all, let me make it clear. So all the integration with ontologies, the plugin to connect with ontologies, the validations, the shackle processing, is done through through an extension called Neo Semantics. That's part of the Neo4j labs. So most of the Neo4j users will be familiar with labs projects like the APOC library of procedures. There's also the streams library that integrate with Kafka. Well, Neo Semantics is similar in the sense that it's a labs project. It's part of this incubator, but it's focused on this integration with semantic technologies. And to answer the question, I would say that probably in terms of the coverage of the shackle language, maybe around 75% of the elements, but in terms of the usage, I mean the usefulness of them, we're probably closer to 90%. I mean there's some elements in shackle that, in the first place, some of them may not make sense in a Neo4j graph, and some others are possible but hardly used, I would say. But in any case, it's a new feature in 4.0. And the coverage will be extended over time. So I would say it's significant, and it's enough to build useful constraint definitions and validations in Neo4j.
Awesome, thanks so much, Marilee.
Hi, thank you, and thank you, Dr. Barrasa, for sharing your expertise. That was great, and thank you, Brenda, for stepping in and facilitating some Q&A today. So I just want to remind you all that if your question wasn't answered, someone from Neo4j will reach out to you directly and get that question answered for you. Thanks for joining us for this great session. We're going to be starting our last session of the day in just a few minutes. So please stay tuned for Empowering Analysts with Graph Visualization. And again, thank you, Dr. Barrasa.
Thank you. My pleasure.